Hi, we are meeting after a long time. I hope all of you are safe and doing well. In this lockdown period, it is better to remain at home. Some of you have requested that I should revise certain portion of classical mechanics. And most of you have requested the second unit, that is the Lagrangian Mechanics. So what I have planned for you is that I will divide this into three parts. The part 1 will be the derivation of Lagrangian equation of motion. Second lecture will be application of this equation of motion. We will solve certain problems. Basically, we have solved them with Newtonian mechanics in lower classes. We will solve with the new method that we are evolving now, and we'll see how it is easy and makes life simple than the Newtonian mechanics. And the third lecture which I have thought of is to devote on deriving conservation laws using cyclic coordinate or ignorable coordinates. So this is what I have planned for you. So let me start with the first lecture today, that is deriving the Lagrangian equation of motion. Lagrangian So let us start with Lagrangian mechanics, and we started this with constraint, and then we went for degrees of freedom, and then we calculated how many generalized coordinates are required for the system. That part I am not revising right now because it's a simple one. I am not going to even do the D-Alembert principle, but I will start with the D-Alembert principle and I will try to derive the Lagrangian equation of motion. So D-Alembert principle is given by summation over I Fi A minus Pi bar dot delta Ri is equal to 0. All of you know that this principle is also called as the principle of virtual work. Fia is the applied force which brings out delta Ri, virtual displacement, and Pi bar is a reverse force which acts so that the system remains in the equilibrium. Now there are two basic problems here. The first basic problem that we are having here is the force itself. So we want equation of motion which will be in a scalar form. So we have to replace this by some scalar quantity, and that is why D-Alembert equation is there, because this is a virtual work and work is a scalar quantity. And next, an important thing that we want to replace here is delta Ri. This delta Ri are Cartesian coordinates, and when the constraints are there, this coordinates get coupled, or equations of motion also get coupled, and solving such equation is a difficult task. So we need to replace them by the generalized coordinates. Generalized coordinates are independent of each other, and therefore we can easily apply the separation of variable and we can solve equations of motion. So let me start with the assumption that there are n degrees of freedom, so I need n generalized coordinates. So let system has n degrees of freedom And let us say q1 comma q2 dot qn are generalized coordinates. So let us take D'Alembert equation as equation number 1. Now this equation of transformation or transformation equation position vector of ith particle will be written as all of you know, position vector we normally write it as symbol Ri, and this will be written as now Ri, but in terms of q1, q2 dot qn, and obviously the time is the n plus 1th variable out there. So any small change in generalized coordinate will bring out small change in Ri as well. So small change in Ri is written as normally we write this as dRi. Since Ri is a function of q1, q2, qn variables, we apply the chain rules to find out the net change in the position of Ri or the ith particle. So this will be written as dou Ri upon dou q1 dq1. So here dou Ri upon dou q1 is the rate of change of position vector of ith particle when small change in q1 is dq1. So again I repeat here, though dRi is the net change in the position of Ri, but since Ri is function of n variable, so every variable will bring out change in Ri. So let us change q1 by dq1. So net change brought by q1 will be dou Ri by dou q1, which is the rate of change of Ri with respect to q1 into the small change that we are carrying out dq1. Similarly, I will write for rest of the variables. I hope all of you are aware of chain rule. So it is not necessary always to write vector Ri. It is assumed that now it is vector. So last variable is time. So I have written that also in terms of time. Now in the short notations we write this as summation over j dou Ri upon dou qz dqz plus dou Ri upon dou t. Now this is the actual change in the position of ith particle. Virtual change is given by, now virtual so let us take this as equation number 3. Virtual displacement we denote it by delta Ri, not by dRi. Virtual displacement does not depend on time. So all of you know this. So the last term in equation 3 will not be present over here, otherwise the things will remain as it is. So delta Ri would be summation over J dou Ri upon dou Qj delta Qj. This is your equation number 4. So having done this, now let us go to the velocity of the particle. Velocity of the particle is given by V bar is dRi upon dt. So if you divide on both sides of equation 3 by dt, we will get this as summation over J dou Ri upon dou Qj. dQj upon dt is Qj dot plus dou Ri upon dou t. And this we also write it as this as Ri dot. Now let us differentiate this with respect to Qj dot. Let us differentiate this with respect to Qj dot. We get dRi bar dot dRi bar dot upon dQj dot. Now this will be equal to, if you take derivative of this term, this is equal to 0. Now derivative of this term, Qj dot derivative will be 1. So I will only have its coefficient dou Ri upon dou Qj. Now you might have realized here that summation sign has disappeared, and this is bound to happen over here. This is because whatever differentiation that we are carrying out, only that variable survives, the rest all will become 0. So this I get this as, so this equation we are going to make use of this, so that is why I have made it pink out there. So let us take this as equation. Now let us go back to the D'Alembert equation. So we have now converted all positions and velocities into the generalized coordinates. Now let us see how can we transform the D'Alembert equation into the generalized coordinates. So D'Alembert principle I rewrite once more. D'Alembert's principle is given by, how do we write it? This is summation over I, Fi applied, Pi bar dot delta Ri is equal to 0. Now let us take first term. Let us take first term. So here now the first term is summation over I Fia dot delta Ri, which is equal to summation over I Fia. Now delta Ri, I replace it by its generalized coordinate transformation equation. So this is summation over j dou Ri upon dou Qj delta Qj. So since I and j are independent of each other, I can write this as summation over j summation over I Fi applied dou Ri upon dou Qj delta Qj. Now this particular quantity here, I call this as Qj, and therefore this whole term becomes summation over j Qj delta Qj with Qj is summation over I Fi dou Ri. So let me just see what was the last number, equation number 5. So let me have this as equation number 6a, and this is equation number 6. Now let me fine. Let us take now the second term. Now let me take the second term. Now the second term here is reverse force that is acting. So Pi bar dot delta Ri. Momentum is mass into velocity. So I will write this as Mi Ri dot. And since there is a force quantity, so it will have a double Ri dot. And delta Ri, again I write this as summation over j dou Ri upon dou Qj delta Qj. So now this I can write this as summation over I summation over j Mi Ri double dot dou Ri upon dou Qj. Now here what I am going to do, I am going to remove one time derivative from this equation. This is the important step in this equation. All of you should pay attention. This is only important and difficult step you can say in this derivation. So if I have to do this, then what I do is, now here onwards I am going to write, it's a matter of convention actually. So I write both summations as I comma j. When I take one derivative out from this term, this will be mi d by dt Ri dot dou Ri upon dou Qj. Now if you expand this term in the u into v form, what you will find here is that you will get one more additional term, and that additional term I should subtract from here, and that makes me to write the second term as Ri dot d by dt dou Ri upon dou Qj delta Qj. Now having done this, now there are two things that I am going to do. From equation 2 or 3, I do not know right now, but I am going to change this as dou Ri dot upon dou Qj dot. And these two derivatives I am going to exchange because they are independent of each other. So if I carry out these two steps in one go, I'll write this as summation over I comma j d by dt. Mass is constant, so mass can always go inside the derivative and it can come out as it likes every time. Ri dot dou Ri bar dot upon dou Qc dot minus, similarly here also, mi Ri dot, if this dou by dou Qc come outside there, and I'll have Ri bar dot delta Qc. Remember, when I interchange the time derivative, Ri will become Ri dot here. So the first term, I'll write one more step here, I comma j. Yeah, this first term I will write it as d by dt. So if I take dou by dou Qj dot outside, then I should have a term containing mi Ri dot square. But square derivative will be 2 Ri dot. So the additional two terms I should remove from here. So I write half here. And I'll have similarly over this term also I can write this as dou by dou Qj mi Ri dot square, and again I will have to divide this by 2 because I'll get additional term when I take the derivative delta Qs. Now I define a term kinetic energy T as summation of all the kinetic energies half mi qi dot Ri dot square. So if I do this now, I will get second term as, let me put this also. So we get this as summation over j, second term, d by dt, dou by dou qj dot t minus dou t by dou qj. So let us give this as equation number 7. Now putting equation 6 and equation 7 in equation 1, substituting equation 6 and 7 in equation. Okay, so let me, as our practice, we'll put this also equation because this is one of the important equation that we are having. So the first term is summation over z qz delta qz minus second term is summation over z d by dt. I'm sorry, this is dou t by dou qz dot minus dou t by dou qz delta qz equal to 0. So which implies this d by dt d by dt for dou t by dou qz dot minus dou t by dou qz is equal to. So this is another important landmark equation out there. So let me mark this. And let us take this as our equation. So this equation we have wrote in terms of the kinetic energy. Now let me bring the potential energy into the picture. So we consider a system is a conservative system. So in the conservative system, force is a function of the gradient of potential. So we just write it as minus of dV by dr. So V is the potential energy of the particle out here. Okay, so let me, since there are Ri, there are various Ri's, so we'll write this as a partial derivative. Remember one thing, V is not a function of any other thing like velocity or any other term. So it is purely a function of Ri only. And then I can write this as, so we know Qz is summation over I Fi A dou Ri dou Qz. So substituting over here, I get this as summation over I minus of dV, I'm sorry, dou V on dou Ri on dou Qz. So which implies that this is equal to minus of, since I term gets cancelled out there, there is no requirement of summation out there, dou V upon dou. So now I'll substitute this in equation 8. But before substituting this in equation 8, I would just add one more thing out here. Q is minus of dou V upon dou Qz. But I'll add one more term out here, dou V upon dou Qz dot. Rather, I'll do it later. Okay. Let us substitute this in equation 8. So if I substitute this in equation 8, I get this as d by dt dou t upon dou qz dot minus of dou t upon dou qz is equal to minus of dou e upon dou qz. So which implies this. The second term, I'll write this as dou of t minus v. When I take this term on the left hand side, I'll get this term upon dou qz, and I'll add one more term here, dou t minus v of qz dot is equal to 0. This I can write because v is function of Ri alone, which implies is dou v upon dou qz dot is equal to 0. So adding or subtracting 0 will not make any difference. So let us take this as equation number 9. So now what I have here is, let me just take define. Let us define a term L. This is Lagrangian, which is equal to t minus v. Rather, in more explicitly, t is a function of q comma q dot, and v is the only function of q naught. So this is equation. So substituting in equation 9, we have d by dt dou L upon dou qz dot minus dou L upon dou qz is equal to 0. This equation is termed as Lagrangian equation of motion. So this is where I will stop it for the day. But what I like all of you to appreciate here is that in Newtonian mechanics, the life was very difficult because it was a force equation. Force has a vector, is a vector quantity, it has a magnitude and it has a direction as well. And when there are n particles interacting with each other, the component of the forces will have to decompose in n directions, and then solving the coupled equation becomes very difficult, and that was the drawback of the Newtonian mechanics. So the solution to it is that we write the differential equation, or we write the equation of motion, which is simpler in the sense it should be in a scalar form. So energy is the quantity which is scalar. And I think so this equation has served that particular purpose, and also we have expressed now equation in the generalized coordinates which do not depend on each other. So with this I will stop for the day over here, and next time we will try to solve some problems which we have solved before again, and we'll see the impact of this equation. Rather, when we solve problems, the importance of the equation comes out. Thanks a lot for the listening to me, and be ready for the next lecture. Before that, you should revise this derivation at least twice or thrice. Thanks a lot.